We now come to the issue of gas laws and how do we analyze things like pressure, temperature, volume, and so forth for ideal gases. Um, so, first things first, when you look at the volume of a gas, okay, when you look at the volume of a gas and you measure the pressure of that gas, you can then adjust the pressure through various means, okay? And then you can measure the resulting volume if your gas is in an expandable container, right? And what you find is that for most gases, okay, for most gases, there's a relationship where your volume is inversely proportional to your pressure. Okay, and I'm going to try to put um, a little line on the bottom of my piece for pressure so that we don't get confused with momentum, which is lowercase p. Um, and so if you were to actually plot the volume versus the pressure, you would actually see, that might be a little steep. It would look something like this. Okay, so this would be a volume and your pressure share an inverse relationship, right? Um, and as a result, this is your inverse law as opposed to an inverse square law, for example, right? But if I then plot the inverse of that, then I get this linear trend, right? I will get this linear trend. Um, and so for most gases, we see this in action, right? And then what you find, if you do a similar experiment with temperature instead, you find that this is linear. So you put a gas in a container with a thermometer, and you then change the temperature through various means, either exposing it to a heat bath or an ice bath, and you can watch the volume change. Right now, we extrapolate um, this kind of experiment all the way back to when the volume reaches zero. And as you can see, when the volume reaches zero, it's very close to a temperature of zero. This is what we call absolute zero. So absolute zero is the temperature that's achieved when your volume goes to zero. Now, in truth, your volume can never go down to exactly zero because molecules and atoms are effectively incompressible. And even if you could compress an atom itself, you couldn't compress the nucleus. And so it does have some finite volume. So the way that we interpret absolute zero now is not so much that the volume of your gas goes to zero at that temperature, but it is the temperature at which atoms and molecules don't have any thermal agitation. Okay, so there's no thermal energy being imparted to them. All right. Um, and so that is how we interpret absolute zero now. You can actually demonstrate this kind of reasoning, okay, with this kind of apparatus. Okay. So suppose I have a flask, and that flask is filled with some sort of gas with a rubber stopper. to seal the container, seal the gas in the container. But I also put a thermometer in the flask as well as a syringe with a needle. Okay. So the syringe with the needle then has access to the gas. So the gas can fill the syringe, right? So first things first, you place this in an ice bath, and sure enough, okay, you'll achieve some sort of temperature. Your thermometer will have some sort of reading, and there will be a certain volume of gas in the syringe. Then you remove the block and remove the ice bath, and then you can put, say, a heat bath, maybe a container filled with boiling water, right? And then replace the block. So now your flask is immersed in boiling water where it had been freezing water before. And you can actually watch the plunger on the syringe lift up. Okay? This is what's known as Charles' Law. Okay? Um, and so if we put these two ideas together, okay, the fact that your volume is proportional to the inverse of your pressure, but it's also proportional to your temperature. Okay, to make this an equality, we insert a proportionality constant. Now, the way that we typically write this, and maybe I shouldn't have used K for my proportionality constant. That might have been a poor choice, as we'll see here in just a moment. So let's maybe write it with capital C. Um, and so we typically write this as V times our pressure is equal to our proportionality constant times our temperature. And it turns out that the proportionality constant, you can actually write it two ways. Okay, the first way is the number of atoms or molecules in your gas, if you know the total number of those molecules, times a well, it's K sub B, and this is why this was a poor choice for K was a poor choice for the proportionality constant a moment ago. Um, N is the total number. Uh, let me rewrite this. So N is the total number of atoms slash molecules, and Kb is what's known as Boltzmann's constant. And this has the value of 1.38 times 10 to the negative 23. Okay. Um, and the units on Boltzmann's constant are joules per Kelvin. Okay, so it's energy per temperature. And when we put this all together, we get the ideal gas law. Okay, now, what is an ideal gas? Okay, so an ideal gas is typically Well, let's. Okay, so for your ideal gas law assumptions, this equation works really, really well if the following two conditions are met. Number one, your gas is fairly rarefied or non dense. And number two, if your gas. Whoop, didn't mean to hit that button. And number two, if your gas is at high temperature. Okay. Now, a number of systems, a lot of gases um, will follow these two assumptions to a very high degree. But I can't stress enough that at the end of the day, these are approximations, or this equation is an approximation. Okay. It just so happens for a very wide variety of gases under the conditions that we would typically interact with them, it's a really, really good approximation. So, for example, we would typically model the atmosphere as an ideal gas for simplicity, and we would get really, really good results with it under most conditions. Okay. Um, and a lot of the gases that you would measure in the laboratory, for example, if you're doing some sort of experiment, particularly at an elementary level, you would get the ideal gas law. Okay. But well, okay. Before we go on, let's kind of state what this means. Okay. Let's state how to use this. If your ideal gas, or if your gas can be modeled as an ideal situation, then what this means is that if I change something like the temperature in the system, okay, then I would have uh, an initial volume, an initial pressure, and an initial temperature. An initial temperature in the system. And then after I change some property, typically you'll change the temperature because that's the easiest to control, and then you measure how the pressure and volume respond. You would have a new volume, you would have a new pressure, and you would have a new temperature. And because if your gas is in a completely sealed container that molecules can't get in or out, then you've fixed the number of molecules. Boltzmann's constant is a constant, so you can also write this as Vp over T equals NKB. So for a given system, if N is constant, then this whole thing is constant. So what that means is this ratio must be true. Okay? V1 P1 over T1 must equal V2 P2 over T2, right? And there we have a relationship that allows us, if we know the inputs of one of the conditions, or one side of this equation, if we know the initial pressure, volume, and temperature, then if we know the secondary volume and pressure, we can calculate the temperature, or if we know the volume and temperature, we can calculate the pressure, or if we know the pressure and temperature, we can calculate the volume, right? So basically, if you know one side of the equation and know something about the other side, you can calculate the remaining quantities. Okay. But again, this is an approximation. So, what happens if we need to expand beyond the ideal gas law? So, this is where we enter with the van der Waals equation of state. And the van der Waal equation of state modifies the ideal gas law ever so slightly. Actually, or not just ever so slightly, but um, first things first, if we relax these two assumptions, okay, let's suppose our gas is dense. Okay. And so what that means is you have a lot more molecules per amount of volume than you do in the ideal gas assumption. Okay. And so with that, you can have um, intermolecular forces, right? So um, as you have these molecules moving around, and they're kind of flying around and bouncing around, in the ideal gas assumption, okay, the ideal there's another assumption that's implicit in here, and that is that as the molecules are flying around, um, the collisions that they would have as they're moving around, all collisions are inelastic. Okay. Um, and that is generally going to be true here, but there are extra attractive forces that the molecules are going to exert on each other as you increase the density. Okay. So as the attractive forces, well, as your density increases, you're increasing you're increasing the number of molecules in your volume, but you're decreasing the space between them, and that allows them to interact gravitationally and electromagnetically in ways that your ideal gas does not. Okay, so you have these increased attractive forces, but because your molecules are more densely packed now, you also have less free space for them to move around in. Okay, so to account for these increased attractive forces, we add this term. And to account for the decrease in available space, we add this term. Okay? Now, the way that we interpret this equation, N is the number of moles in the gas. Okay? And so remember that 1 mole contains 6.02 times 10 to the 23rd molecules or atoms or whatever your substance is made of. Okay? Um, and R is what's known as the gas constant. Okay? And you'll notice that the right-hand side, nRT, kind of resembles and in fact they are equivalent. Okay, so N is the number of moles in my gas, lowercase n, but remember capital N was the total number of um, either atoms or molecules. So if I take Avogadro's number, then the total number of atoms or molecules divided by Avogadro's number gives me the number of moles. Okay? So what this means is that if I have NKBT and I multiply by 1 in the form of Na over Na, then this becomes lowercase n, Na times Kb becomes R, and T stays T. Okay, so your gas constant R is equal to Avogadro's number times Boltzmann's constant. Okay, so that's all that's going on the right-hand side. We're kind of moving from looking at things in terms of the total number of molecules to the number of moles. Okay, so coming back to the left-hand side of the van der Waals equation, we have our pressure minus A times N over V quantity squared. Okay, so remember that force is equal to pressure times area. Okay, and so pressure, I really should have written that as pressure equals force divided by area. Okay, so if we're taking the increased attractive forces into account, this is the term that does that. Okay, so your total pressure in your system is going to be equal to the pressure of the system as you would measure relative to vacuum minus the force per unit area on average that the molecules are exerting on each other. And the way to measure that is to look at the ratio of the moles to volume and A is a coefficient to be determined by experiment. And it's unique for each gas, each element, each gas, because we can say that it's unique to each element slash molecule or combination of. So we can just say that it's unique for each kind of gas that you would measure. Okay, so you would actually have to go into the laboratory and fit this with an equation and find A experimentally. Okay. And these forces, because they're attractive, they decrease the pressure. They're pulling the molecules toward each other, and that's why this is a minus sign. Okay. So this is your pressure relative to vacuum. And these are this is the pressure or the reduction in pressure, we should say. Okay, so this is the reduction in pressure due to the intermolecular forces. Um, and B, so you can think of B as the volume per molecule. Well, technically volume per mole. Okay, and then of course N is the number of moles. So, because as your gas is not as rarefied, it's more dense, each molecule is going to be packed closer with other molecules, and therefore the total volume of the molecules themselves is no longer negligible. In the ideal gas case, we really don't care about the volume of an individual atom compared to the total amount of space that it has to move around in. Even if it's going to collide with other atoms, we really don't care about the volume uh, of the atoms themselves. But here, when your gas is more dense, you have to take that into account. And so this is the volume of your container. And this is the volume of your molecules. And so V minus B, or V minus NB, is the uh, uh, volume the molecules can move around in. Okay. And so this equation is still not the end of the story. This is still an approximation. But it is a darn good approximation. Okay. It is a darn good approximation. So, with that, um, these are really the only two laws that we are going to have any dealings with whatsoever. But this is where these two laws, or not necessarily the rigorous derivations behind them, but at least some justification for where they come from, right? So with that, we will be done with gas laws. Well, at least in presenting them here in the lectures. And up next, we will start to look at how to relate temperature to the kinetic energy of your molecules in your gas. All right, so stay tuned.